Hello, everyone. I'm glad to be here today to tell you about the impact of third-party code on Android app security. So let's get started. Third-party code is a double-edged sword. On the one hand, it has become an indispensable aspect of modern software development. It eases the development process by allowing to reuse existing code, which usually results in faster development and reduced development costs. On the other hand, it also increases the app's attack surface as code from different origins is used. And such code may differ in terms of quality, maintenance, and reliability. If further closed source components are used, application developers must also trust library providers to adhere to security and privacy best practices. But now let's put at risk in numbers. According to the Central Repository, the largest open source component repository, more than 2 billion software components with known security vulnerabilities are downloaded each and every year. They further report that outdated libraries have a 3 times higher risk of being vulnerable as compared to up-to-date versions. And there's also the prominent overview list of the top 10 security risks. And since 2013, it includes a risk entitled using components with known vulnerabilities to warn application developers about the emerging threat of using insecure third-party code. But these are only risk estimations. What we actually want to do is to quantify the security impact of third-party code. And to do so, we have to perform the 3 following tasks. First, we need to measure the status quo of library outdatedness in the software ecosystem. Second, we need to identify those applications that use library versions with known security vulnerabilities. And third, whenever we find a new vulnerability, a security or privacy issue, we want to properly attribute this issue to the correct application component. So either the application code or some library code. And all those 3 tasks have in common that they require a reliable detection of third-party code in applications. So in the following, I will show you the example of Android, the largest mobile software ecosystem, on how to quantify the security impact. Why Android? Because it poses a variety of challenges on the detection of third-party code in the application binaries. And these challenges can be explained best by looking at how these libraries are integrated during the development process. So at first, we have the developer view, which is very explicit. So the developer knows which libraries are included, which versions thereof, and you might also know the origins of these libraries. But as soon as the app is compiled, this explicit mapping gets lost, as any third-party code is now statically linked to the application code. And as a result, we receive one monolithic bytecode file. And we do not longer have different code origins. And this has severe security implications, because now any third-party library that is included inherits the access rights and permissions of their host application. So if the host app is able to access sensitive data, like your location or your contact data, so does each and every included library. And past incidents have shown that in particular a number of advertisement and tracking libraries misuse these inherited access rights to steal personal data and to track the user. But we are not yet at the end of the story. Because in Android, the majority of apps is either partially or fully obfuscated. Because in Android app development, obfuscation techniques are rather the default than the exception. And among the 2 most commonly used obfuscation techniques, there are identifier renaming and dead code elimination. So in identifier renaming, identifiers like the method name, the class name, or even entire packages and namespaces are transformed into short, non-meaningful character sequences. For instance, a namespace like com.google would then be transformed into something like a.b. And then we have that code elimination. application developers typically don't make use of the entire library functionality. They are only using a subset thereof. So that code elimination then strips any unused functionality from the application binary. And as a result, we are now facing another detection challenge. We must not only detect the original library in the application, but also subsets thereof. And these subsets may change for each and every application. So the bottom line is that these obfuscation techniques further blur the boundary between application and library code. And the question is, how can we approach these challenges? A common way to do so is to conduct a static code analysis. In this case, it would be a bytecode analysis, as for the majority of Android apps, the source code is not available. And in the first step, you will then create the appropriate data structures, for instance, a control flow graph. Now, you can refine your analysis by adding call edges to retrieve a call graph. However, as soon as you have to analyze specific code instructions, you may also run into problems, like in this case, obfuscated calls. Then you're no longer able to statically determine the receiving ends of these calls. And as a result, you add imprecision to your data structures, although you spend an additional amount of effort into their generation. And this additional effort also negatively influences the scalability of your approach. And scalability is important because we are talking about more than 3 million applications just hosted on the Google Play Store. So it turns out that these common analysis approaches do not fit well to our requirements. And we have to get back to the drawing board and come up with a novel idea that in the best case combines both precision and scalability. So we asked ourselves, is it possible to detect third-party code by just looking at the code structure? And with that, eliminating the need to analyze specific code instructions. So let's see what happens if we remove code instructions. What is left is a set of method signatures. A method signature comprises the method name, the argument type list, and the return type. Now, if we zoom out a bit, we further see the enclosing class and a package name, a namespace. Android apps and libraries are written in Java, and Java code is organized in hierarchical namespaces. Now, the key observation is that these namespaces, in contrast to native code, are preserved in the application binaries. So we can leverage that fact and pass these namespaces and represent them as a package tree. Now, as we continue to do so for the remaining classes of the application, we eventually receive a complete package tree that represents the code structure of the application we are looking for. However, we cannot rely on any of these identifiers because they are all subject to identifier renaming. Instead, we must only leverage the structure for detection. But how can we do this? We can do this by transforming this package tree into a Merkle tree. A Merkle tree is basically a hash tree where parent nodes are generated from its child nodes. And Merkle trees are typically used for efficient integrity checks for large data structures and file systems. So here we can transform this package tree into a 3-layered Merkle tree, having dedicated layers for packages, classes, and methods. Now, these trees are built bottom-up, starting with the method hashes. And we can sort them before generating the parent hash to retrieve a deterministic build order. Now, as soon as these trees are built, we can compare different trees in a bottom-up manner, starting with the package hashes. So now the only question that is left open is, how do we start? So how do we generate the method hashes? A simple approach would be to take the method signature and hash it. But then we would be again prone to identifier renaming. So we have to tweak it a bit to make it resistant against that kind of obfuscation. And we can do so by applying a simple 2-step approach. First, we remove anything before the brackets, leaving only the argument type list and the return type. In the second step, we replace any custom type with a common placeholder value x. So here, we do not distinguish between different types. We are only interested in the number of types we replaced and their position. what we receive is a so-called fuzzy descriptor. You can think of it as a pattern or a template. Now, at that point, we intentionally introduced an error to defeat the obfuscation, because obviously, this fuzzy descriptor does not only match the original signature, but it would also match similar signatures. But the good thing is that while we are building the tree, this error will decrease because we are adding more and more methods, more and more classes, and more packages. And eventually, we receive a unique Merkle tree that represents a profile for our library. Now, having these profiles, how can we leverage them for detection? The idea is the following. First, we create a database of libraries and library versions. And then for each library version, we generate a profile. So for efficiency reasons, we can strip the method layer, as that code elimination only operates on package and class layer. We then do the same for all applications under test. And then we can check for each library version whether its set of package hashes is included in the application. If this is the case, we can already stop here because we have a full match, meaning that the complete original library version is included in the application. Now, in case of a partial match, we can now go one level deeper in the tree and check whether the library classes are included in the application. So in that case, we would find a package in the application that contains 2 out of 3 classes. For instance, because the third class has been stripped by the dead code elimination. We would then report a partial match and further indicate the fraction of the original library code that is included in the application. So now, having a reliable approach to detect libraries, even in spite of commonly used obfuscation techniques, we can now go on to quantify the security impact of third-party libraries. And we can start doing so by measuring the library outdatedness in apps. And to that end, we took the Facebook SDK, one of the most widely used libraries in Android app development. So on the y-axis, you see the different versions of these libraries, having the most current version on top. And these library versions span over a period of about 5 years. Now, when adding the results, you can see a very high fragmentation, meaning that each and every library version that exists is actually being used by applications. Now, the surprising fact is that these are not the results for all applications in the Google Play Store, but only for the top 4,000 applications. And for such applications, you would certainly expect to have a proper code maintenance. And in fact, they have, but only for the application code and not for the included libraries. And by measuring the outdatedness, we can also check for library versions with known security vulnerabilities. So in version 3.15 of the Facebook SDK, there has been a severe account hijacking vulnerability. And as you can see, even in the most current version of these top apps, there's still a significant number that includes this vulnerable third-party code. Now, as said, these results only reflect the most current version of each application. But we are also interested in measuring the vulnerability lifetime. To that end, we took the set of applications, and for each application, we crawled its entire version history. And we then checked at which point in time this vulnerable SDK was introduced, and in which point in time it was eventually fixed. So in this graph, you see a time frame of about 2 years, starting with the release of the vulnerable SDK in June 2014. About 1 month later, the fixed version was released. Now on the y-axis, you see the number of released apps with this vulnerable SDK per day. Obviously, within that 1 month's time frame, there has been a number of apps released that include this vulnerable code. But now with the release of the patch, you would certainly expect a fast decline in the number of apps. But unfortunately, the reality looks different. So there's even a short increase in the number of apps that include this vulnerable code. And even after a 1-year time period, there's still a significant number of new apps and app updates that include this vulnerable version. Now, when looking at the fixing rate, you can only see a very small number that actually fixes this problem, either by updating to a non-vulnerable version or by removing the SDK completely, which in that case is also a valid fix. And this reinforces our assumption that although application code is properly maintained, the included libraries are not, even in the presence of a severe security vulnerability. Now, we have seen a lot of issues with third-party code and outdated libraries. But how can we remedy this situation? A simple approach would be to point with the fingers at application developers and say, do your job, update your dependencies, and we don't have a problem. But I would argue that this is a very naive approach because application developers are just one contributing factor to this overall problem. And there exist many more actors in the Android ecosystem that similarly contribute. And one of these actors is the library developer. Library developers often make it hard to adopt security patches because they are mixing security updates with new functionality, and they even remove existing functionality, rendering the update incompatible to the current version. And as a result, application developers have to spend an additional amount of effort into adopting the security patch. I would further argue that Android needs additional platform support. In contrast to other mature ecosystems like iOS or JavaScript, Android does not have a dedicated package manager. And these are important for app developers to conveniently search for and compare different third-party libraries. And then there's also a need for improved development tools. So application developers are typically good at programming, but they have only a very limited knowledge in security. So if you require them to keep their dependencies up to date, you should also equip them with the appropriate development tools. And such tools should warn them whenever they are using library versions with known security vulnerabilities, and they should tell them to which extent they can update outdated libraries without having to adapt and refactor application code. And finally, there are the market operators. The market operators should adopt state-of-the-art analyses to improve their application vetting and catch security issues that haven't been identified during the development process. Okay, so we have seen that third-party libraries are indeed a double-edged sword. But does it mean that we should no longer use them? Well, absolutely not. But whenever we are using them, we should always keep in mind potential security implications. Now in this talk, I presented a novel library detection approach that even works in spite of commonly used obfuscation techniques. And with that approach, we could for the first time quantify the security impact of third-party code in Android apps. Now, with that, we also raise the awareness for this problem, and I hope that our approach can also form the foundation for more advanced app analyses and improved development tools. And finally, there is no silver bullet for this problem. While there exists a number of short-term actions that can remedy the situation to a certain extent, it really requires the combined effort of different actors of the Android ecosystem to improve on the current status quo more sustainably. Thank you.